These are part 1 of the notes for AP Calculus on the topic of related rates. So in related rates, what we're going to use is implicit differentiation for things that are oftentimes not functions to find the rate of change or derivative, or rate of change is another word for the derivative, of 2 or more variables that are changing with respect to time. Okay. So these are the kind of general steps we're going to go through on most of these problems. So if you get stuck as you're going along and you can't remember what to do next, you can kind of refer back to these steps to figure out where you're at in the problem. But let's jump into some example problems here. This first one says we've got a rocket rising vertically is tracked by a radar station that is on the ground 5 miles from the launch pad. How fast is the rocket rising when it is 4 miles high and its distance from the radar station is increasing at a rate of 2,000 miles per hour? Okay, so let's first try to, on most of these problems, there's going to be some kind of a diagram we can draw. And you don't have to be a good artist to do this. You just have to kind of just draw the situation here. So we've got this rocket here. So there's my rocket. And it's rising vertically. And it's tracked by a radar station on the ground 5 miles from the launch pad. So rising vertically there, we've got some launch pad here. And if you don't know how to draw something, you can always just label what it is. So I don't really know how to draw a launch pad. Okay, so I'm just going to label it. Okay, there's my launch pad. And then it's tracked by a radar station that's on the ground 5 miles from the launch pad. So over here we've got, I don't really know how to draw a radar station. It's supposed to be a satellite dish there. So again, you can always write down what it is if you can't draw it. That says that's 5 miles from the launch pad. So to figure out, usually the most challenging part of these problems is figuring out how to label your diagram and how to start setting it up. So first you want to see, is there anything that's going to remain constant in the problem that's not changing? And this particular problem, it says the radar station's on the ground 5 miles from the launch pad. So that's not changing. So in our diagram, we don't need to assign a variable there. We can call that 5, because that's a constant. And then to figure out where to assign your variable, it's based on the rates you know and the rates you're given. So we're looking for how fast is the rocket rising when it is 4 miles high, and its distance from the radar station is increasing at a rate of 2,000 miles per hour. So it says it's referring to the rocket. Distance from the radar station is increasing at a rate of 2,000 miles per hour. So here's our rocket. Its distance from the radar station. Well, that would indicate we need to draw some line here that connects those two. And if we want its distance from the radar station, if we know its rate, we need to call out some variable. So I'll call this, say, x. So if I call that x, then what this is giving us is how that variable is changing over time. It's changing, increasing at a rate of 2,000 miles per hour. So the calculus expression we're given there is the x dt. We need a variable here before we can write it. You can call it whatever you want. In this case, I call it x. And since x is getting bigger, since the rocket's rising, the rate is going to be a positive 2,000 miles per hour. If the rocket was falling to the ground and x was getting smaller, then it would be a negative 2,000. So that's the rate we know. That's one way you can figure out where to assign your variable. You need a variable so you can represent a rate you know. And you also need variables for the rates you're looking for. It says, how fast is the rocket rising? Well, how it's rising is the change in this distance right here from the rocket to the launch pad. So I'm going to call that h. So if that's h, then what we're looking for is how h is changing. So how fast is it rising? We're looking for dh dt. That's the rate we're trying to find, so I'm going to put equals question mark. And specifically, when it's 4 miles high. So specifically when h equals 4. But it's important not to put 4 right here in our diagram, because then it would represent that the rocket's always 4 miles high, which is not the case. It's changing. What we'll use that for is after we take the derivative, not before. So now let's look at our diagram. And let's set up an equation that would relate h with x. So in this case, you can see we've got a right triangle here, so we can use the Pythagorean theorem. So we can say h squared plus this side, the big squared, is 5 squared, equals the hypotenuse x squared. Okay. So that's the equation that relates them. And then in order to get dh dt and dx dt in the equation, that's where we take the derivatives. This is where we use implicit differentiation. Because again, oftentimes these are not functions. But the difference is we take the derivative with respect to t. Not with respect to x or respect to h, because we want dx dt and dh dt in there. So again, the normal rules for derivatives apply. The derivative of h squared using the power would be 2h. But with implicit differentiation, every time this variable doesn't match up with the variable you take the derivative of, in this case it's h and t, you need to multiply it by the derivative, in this case, dh dt. We'll see why a little bit later, why that's necessary. Plus, well, the derivative of 5 squared, that's just a constant, is 0. And the derivative of x squared, using the power, would be 2x, but again, x doesn't match up with the t, so we'd also need to multiply that by dx dt. Then, after you take the derivative, then you can plug in all the information you know. So let's see, do we know h? Yes. Now we can plug in h's form. dh dt, do we know that? No, that's what we're looking for, so we'll leave that dh dt equals 2. See, do we know what x is? No, we don't know what x is yet. And dx dt, though, we know is 2,000. So now you can see, well, is there anything else we need to know in order to solve for, in this case, dh dt? Looks like we have everything we need except we need to know what x is. So usually when you're missing a piece of information, where you go is back to the original equation. So since we're missing this x, let's go back to the original equation off to the side here. And now we can plug in 4 for h, because we've already taken the derivative. And say, well, we've got h is 4, so 4 squared plus 5 squared would have to equal x squared. And now we have an equation using the Pythagorean theorem, we can solve for x. So let's see, 4 squared gives you 16, plus 5 squared is 25, equals x squared. 16 plus 25 gives you 41. And then to solve, last step to solve for x, you just take the square root of both sides. Normally you take the square root of both sides, x would equal plus or minus the square root of 41. But in this case, based on our diagram, we can see it wouldn't make sense for x to be negative. So it's on the distance. Distances can't be negative, so it would just be minus the square root of 41. In this case, that doesn't simplify any further. So now we know what x is, so we can substitute that right back in here. And then we'll have everything we need to solve for dh dt. So we have 4 times 2 is 8 times dh dt equals, well, 2,000 times 2 is 4,000. And we just figured out x is the square root of 41. And then the last step to solve for dh dt, you would just divide by 8. So dh dt, 4,000 divided by 8, well, 40 divided by 8 is 5, just add 2 zeros there, so it'd be 500. And then times the square root of 41. And that's the exact answer. You can leave it in that form. If you want to work out as a decimal using your calculator, you can. If you do that, make sure you're accurate to the thousandths place, to 3 decimal places. But there's no need to really do that. We can leave it like that. So, to figure out the correct units, all you have to do is look at the units of the 2 variables in your expression. So let's do units for h. Well, h is this distance here. You can see the units for distance in this problem are miles. So this would be miles. And then per, and the units for t is time in this problem. Time, you can see, is in terms of hours in this problem. So it'd be miles per hour. Okay, and you can see we got a positive answer because h is getting bigger. All right, let's take a look at another example. On this next one, it says the height of a triangle is decreasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the height is 10 centimeters and the area is 100 centimeters squared? So it doesn't say it's a right triangle here, so we just have some triangle. We'll just draw some triangle here. So I've got some triangle there, and to see where you assign your variables, it's based on the rates you're given and the rates you're looking for. So let's start with the first thing we're told here. It's the height of the triangles decreasing at a rate of 1 centimeter per minute. So that tells us we need to label the height. I'll call it h for height, make it simple. So what it's giving us there is dh dt. But notice the key word here is it tells us it's decreasing at a rate of 1 centimeter per minute. So if something's decreasing, it's getting smaller, that means the rate, or the rate of change, is going to be negative. So in this case, dh dt would be actually negative 1. So that's one rate we're given. But in this problem, we're actually given a second rate. We're also told the area of the triangle is increasing at a rate of 2 centimeters squared per minute. Another way to tell us the area, look, the unit centimeters squared, that's two-dimensional, right? So that's area per minute, as opposed to height, which is centimeters, because that's one-dimensional. So this is giving us, now A, really that just represents the area of the triangle. It's not really something you need to label on your diagram. But usually we use capital A, so it would be d capital A dt. That's another rate we're given. Notice here it says it's increasing. So that means it's getting larger, so your rate of change is going to be positive, in this case positive 2. So those are the two rates we know. Now let's look for the rate we're trying to find. It says at what rate is the base of the triangle changing when the height is 10 centimeters and the area is 100 centimeters squared? So what we're trying to find is the rate of change of the base of the triangle. So I'm going to label B to represent the base of the triangle there. So what we're trying to find is how that's changing. So we're trying to find dB dt. Specifically when the height is 10, so when h is 10, and when the area is 100. But again, we're not going to put in h for 10 in our diagram or a is 100 until after we take it. So this time, again, we need an equation that relates the variables and the rates we know and the rates we're given. So here we've got the area, the base, and the height. So to relate those three variables, we need to use the area of a triangle formula. So the area of a triangle is 1/2 the base times the height. And since we know dA dt, and we know dH dt, and we're looking for dB dt, we can take the derivative right here with respect to time to get those rates in there. So the derivative of A, well, that would just be 1, but then we would need, if the variables don't match up, dA dt, plus differentiation, and then equals, and then in order to take the derivative of 1/2 b times h, that's where we're going to have to use the product rule. We treat the first function as 1/2 b, and the second function as h. So remember the product rule. First you take the derivative of the first term, so the derivative of 1/2 b would just be 1/2, but then we need dB dt, since the variables don't match up there, times, the product rule says the derivative of the first one times the second one as it is, so times h as it is, and then the product rule says plus the first one as it is, which is 1/2 b, times the derivative of the second one. Derivative of h is just 1, but then the variables don't match up, so we took the derivative of h term, so we need dH dt. And again, after you take the derivative, then you can plug in everything you know. So dA dt we know is 2 equals 1/2 dB dt, that's what we're looking for, so we don't know that yet. H is 10, so we'll plug in 10 for H. B, we don't know the value of B yet, so we'll leave that at B. And dH dt we know is -1. Okay, so if we take a look here, we know pretty much everything we need to solve for dB dt, except we don't know what B is, right? If we have B, then we do have everything we need to solve for dB dt. So again, usually when you're missing a piece of information, where you go to find it is back to the original equation here. So let's see. We go back to original equation, we can know the area is 100. That equals 1/2 times the base is what we're trying to figure out, and we know the height is 10. So we can use this to solve for B. So we've got 100 equals 10 times 1/2 is 5, so that's 5B. And then just divide by 5. 100 divided by 5 is 20. So we get the base is 20. Now we can take that and substitute it right back in here. And then we'll have everything we need to solve for dB dt. So we've got 2 equals 10 times 1/2 is 5. And then we've got dB dt. And then here we've got 20 times 1/2 is 10, times -1 is -10. And now if you just solve for dB dt, to isolate it, add the 10. So we get 2 plus 10 is 12, equals 5, times dB dt. And then when you divide by 5, switch the sides here, you get dB dt equals 12/5. But again, we need the correct units. So again, just look right here at your expression. The units for the base, well, that base is a length, and just like the height is a length, that's in terms of centimeters. And the units for time in this problem, you can see the rates are in terms of centimeters or centimeters squared per minute, so the units for time are minutes, so centimeters per minute. And let's see if having a positive answer makes sense here. That means the base is getting larger. So it says the height's decreasing while the area is increasing. Well, if the height's decreasing, that would normally make the area get smaller as well, but it says the area is increasing. So the only way that can happen is if the base is increasing. If the base was decreasing and the height was decreasing, then the area would be decreasing. So we would need to get a positive answer there, which we did. Okay, let's take a look at another example now. On this one it says we've got a tank in the shape of a right circular cone that's being filled with water at a rate of 13 cubic feet per minute. It also has a small leak in the bottom that's leaking at a rate of 1 cubic foot per minute. All right, so let's start to draw what this looks like here. So it's a right circular cone. There's our cone. And it says it's being filled with water at a rate of 13 cubic feet per minute. So there's water going in, 13 cubic feet per minute. But it also has a leak in the bottom. It's leaking out at 1 cubic foot per minute. Okay. And it also gives us the dimensions. It says the height is 30 and the radius is 15. So the radius of the 15, the height, there's 30. And it says in order to collect the water that leaks out of the tank, a barrel in the shape of a right circular cylinder is placed below the leak. The barrel has a height of 5 feet and a radius of 3 feet. So we've got underneath this some barrel here, the shape of a right circular cylinder. And it has a height of 5 feet and a radius of 3 feet. So that's our situation. So let's first think about how we can represent the rate we know. In part A, we're asked about write an expression for the rate of change of the depth of the water in the center of the cone in terms of the depth. Okay. So let's try to write that here. The depth of the water in the center of the cone. Well, we've got some amount of water inside this cone here. And that forms like a mini cone inside the big cone. And we want to know the rate of change or derivative of the depth of the water in the center of the cone. So usually what we refer to that is as the height, h. And we're trying to find its rate of change. So what we're looking for here in part A, so we're trying to find dHdt. And then notice it says in terms of the depth, which we call h. So our answer is going to have h in it. We're not going to get a specific number like we did in the previous two problems, like 5 or -2. We're just going to get something that has h in it. Now, let's figure out, so that's the rate we're looking for, let's figure out what the rate is we're given. We're given it, so the water is going in at 13 cubic feet per minute, and it's leaking out of the cone at 1 cubic foot per minute. So notice the clue there is the units. They're both in cubic feet. And we know what's in cubic feet, that's volume. That's the volume of the water. So what we're given is, we use capital V for the volume of the water in the cone, dV dt. But there's two different rates here, right? It's going in at 13 cubic feet per minute. Meanwhile, it's leaking out at 1 cubic foot per minute. So just put those together, it would just be 13 minus 1. So the overall rate of change of the volume of water in the cone would be 12 cubic feet per minute. So that's the rate we know, and dHdt is the rate we're looking for. So the equation that we relate those to help us solve for dHdt is the volume of a cone. So remember the volume of a cone formula. It's 1/3 pi r squared h. However, we don't want to take the derivative right now. Okay? The reason why is we have dV dt, right? We're looking for dHdt, but notice we've got this r in here also. We don't have drdt, and we're not looking for drdt. So if we take the derivative right now, we're going to get stuck with the drdt in there that we're not looking for, and we don't know. So we'll get stuck and we'll be able to solve it. So that tells us before we take the derivative, we need to figure out a way to get the r out of there. And the way that we do that with a cone, well, we know the radius of a cone, well, it's going to be changing depending on the level of the water in there. However, it's going to fit, if we draw it right here, we've really got a situation of similar triangles, where here's our little triangle, which is represents the cone of the water in there, and then we've got the dimensions of the big triangle, which is 15 and 30. So using the proportions to set up an equation for similar triangles, we can say in the little cone, r over h corresponds to the big cone, 15 over 30. And then since we're trying to get the r out of this equation before we take the derivative, we want to solve this expression for r. So if we first cross multiply, say 30 times r would have to equal 15 times h, and then divide by 30. You could leave it like that, but that reduces. 15 goes into 30 twice, so r is the same as h over 2. And now we can take that expression, h over 2, for r, and substitute it in to our volume equation to get rid of the r before we take the derivative. So now our volume for the cone, I'll just write this as pi over 3, just a little more compactly. And then instead of r, we just figured out that's h over 2. So we have h over 2, but notice the radius is squared times h. So now you could take the derivative here, but let's try to make it as simple as possible before we take the derivative. So first, let's go ahead and square that out. So we have pi over 3 times, when you square that out, that's h squared over 2 squared is 4 times h. And again, we can make that even simpler by pulling everything that's a constant out in front. So we can pull that 4 out with a 3. So our constant in this problem out in front is pi over 12. And then we've got h squared times h is h cubed. So now notice there's no more r in there, right? We just have an equation that relates d and h. That's good because we know dV dt and we're looking for dHdt. So now is when you would take the derivative with respect to t. So the derivative of v would just be 1, but then the variables don't match up, so that's what we need dv dt equals pi over 12 h cubed. That's where you'd use the power rule. So you bring down the 3 times pi over 12. Well, 3 goes into 12 4 times, so that would reduce it to pi over 4. And then exponent reduces by 1, h squared. But then we need, since h doesn't match up with t, dh dt. Then we can plug in what we know. We know dv dt is 12. And I'm going to just write this a little way that's going to be a little easier for our next step. It's pi h squared over 4 times dh dt. And remember, it said our answer is going to be in terms of the depth h. So we don't need to know what h is here and go back to the original equation to find it. We can have h in our answer. So all we have to do now to solve for dh dt, to isolate it, I wrote it like this, so it's easy to see. Well, you can just multiply by the reciprocal. We need to divide that. So it's like multiplying by 4 over pi h squared. And then to balance it out, you have to multiply the other side by 4 over pi h squared. So when you do that, the 4 and the pi h squareds cancel out, just leave you with dh dt on this side. Just going to switch sides here. And then here, 12 times 4 is 48 over pi h squared. And when you don't have a specific answer, when you have in terms of number, you don't have to put the answer unless it specifically says to. So we can just leave our answer as 48 over pi h squared. Now, let's think about if this makes sense here. What this is saying is dh dt depends upon the value of h. And as h gets bigger, this is on the denominator and it's squared, dh dt is actually going to get smaller as h gets bigger. Let's see if that makes sense. Well, think about if this cone starts out being empty. When you first start pouring it in, because there's not much volume at the bottom there, it's pretty narrow, the height's going to increase pretty quickly. But as h gets larger, then the height's not going to increase as quickly because there's more volume towards the top here. So that's what this expression is showing us. As h is actually getting bigger, dh dt, the rate of change of the height, is getting smaller. But it is positive because h is getting bigger. Now let's take a look at part B, which deals with the cylindrical barrel. So it says find the rate of change, another word for the derivative, of the depth of the water in the cylinder. So normally I would just call that h, but we've already used h in our cone, so I don't want to get those mixed up accidentally. So we've got some amount of water that's dripping out of the cone into the cylinder. So I'm going to call that height there just h sub 1. So we can still use the letter h, but distinguish it from the height of our cone there. So what we're trying to find is its derivative, its rate of change. So we're looking for dh sub 1 dt. And the rate we know is dv dt, but let's see, would it be the same for the cone as it is for the cylinder or not? So for the cylinder, notice for the cone it's going in at 13, coming out at 1. So we did 13 minus 1. But for the cylinder, the only thing that affects is this 1 that's going into the cylinder. And it's negative in terms of the cone because it's leaking out of the cone, but in terms of the cylinder, it's actually positive. So our dv dt here, although I'm not going to use v again because that was the volume of the cone, I'm going to use v sub 1, would be positive 1 because it's going into the cylinder at a positive rate of 1 cubic foot per minute. So now, what equation would relate the volume of the cylinder to the height of the cylinder? That would be the volume of the cylinder formula. So that would be here v sub 1 equals pi r squared h, but here we've got h sub 1 instead of h. But again, just like the cone, if you take the derivative right now, you're going to get stuck because we have dv dt, we're looking for dh sub 1 dt, we have v sub 1 dt, but we don't know dr dt and we're not looking for it. So on this one, again, the way you get it out of there, well, first you have to get it out of there before you take the derivative. But this is a container here, right? It's a barrel. It's a little simpler than the cone. Notice, unlike the cone where the radius changes as the height changes, right? For a cylinder, no matter what the height is there, you can see since it's a container, the radius is always going to stay 3. So because of that, the radius for the cylinder is actually a constant, and we can just substitute it right in before we take the derivative. So we can say v sub 1 equals pi times 3 squared times h sub 1. And the radius is always 3 on the cylinder. And then we can simplify that. So v sub 1 equals 3 squared is 9, so that would be 9 pi times h sub 1. Now we can take the derivative, because now we just have the variables that we either know their rates or we're looking for the rates. We know dv sub 1 dt and we're looking for dh sub 1 dt. So now let's take the derivative with respect to time. The derivative of v sub 1 again would just be 1, but then we need, since it's implicit differentiation, dv sub 1 dt equal to the derivative of 9 pi h sub 1. 9 pi is just a constant, right, on the front. So just like the derivative of 5h would be 5, the derivative of 9 pi h would be, h sub 1 would be 9 pi. But then we need the derivative of that, so it'd be dh sub 1 dt. It doesn't match up with the t. And then we can plug in what we know. We know dv sub 1 dt is 1. And then all you have to do to solve for dh sub 1 dt is divide by 9 pi. So we get dh sub 1 dt is just 1 over 9 pi. And the units, well, the units for height in this problem, you can see our volumes in feet cubed, so height would just be one-dimensional feet. And the units for time, the rates are in feet cubed per minute, so the units for time are minutes. And you can see we got a positive answer here. Let's see if that makes sense. That means the height that water in the cylinder is increased, and it is because it's going into the cylinder at 1 cubic foot per minute. And that concludes part 1 of the notes on related rates for AP Calc.